Should I be talking a little bit about materials in the book of Griffiths? It's not a terribly high level book, but still gives a good comprehensive view of the topics, of the calculations and things that you can follow because there's very explicit algebra in this book. So it's like some kind of super fast express going through the book, almost good parts of it, and you will see that and a little bit more. Essentially, the whole book will be covered, at least a good part of it. So just to recall and just go through the chapters in the book, he also introduces units which are very useful for us. So this is times 10 to the minus 19 joules, as you know, and we all know that the various scales. EV scale is atomic physics. Atomic physics. We know that KeV is molecular, weak molecular and nuclear physics. Not really molecular, but more nuclear physics. And GeV, and these days TeV is very good particle physics. And at much, much higher scale, 10 to the 19 GeV is where you're supposed to do lump physics. But we haven't got there yet. And he also reminds us that the mass of the proton, 938 MeV, c squared, 1.7 times 10 to the minus 24 grams. These are all things that all of you should know by now. He also mentions uh, the units used for electrodynamics, and in these units, E squared by 4 pi alpha is on a French construct constant. He also mentions that historically the photon really proved by Compton scattering. And you may say it was also proved by photoelectric effect Compton scattering. It is very important because it allows us to define the basic length scale whenever we have particles. And this, of course, is related to the scattering of, let's say, a photon on a particle that's at rest in the laboratory. And after that, it just scatters like this to here. Photon with a changed momentum, and then this is the particle which goes off after scattering in example theta. And this is how you see the rise of the Compton wavelength, which is lambda prime, which is the wavelength of this outgoing photon is lambda plus c times 1 minus cosine theta. So this is good to know where this is coming from. The Compton wavelength is h by c, the fundamental length scale as far as we are concerned. And the study of particle physics, a standard model, concerns the study of leptons and, of course, mesons and baryons. And today we know also force carriers. So this was the old story. So today we also have to add force carriers. We also have to add the Higgs boson. So if you look at old books written before 2012, they all stop with this. There's never any mention of Higgs. But today we have to include the study of the Higgs also in the standard model. So this is, of course, flavor diagonal. Flavor diagonal. If you start out with an electron, the electron stays. So you already see the example of electron number conservation. Electron number. So this is in the electromagnetic interaction, and electron number of each type separately is conserved. But today we know that the weak interactions, they change the type of flare of electron. Type of electron is changed. Give me an example where we have a mu going to new mu, and then we have an electron and an neutrino. So we have electron number conservation at each vertex. The type of electron number is conserved, but the particle type changes. Okay, so this is the charge current interaction which changes the type. Mu is also anti. No, if it's a mu minus, say that again. Why? If it's muon type, then it has to stay in mu only. No? I'm looking at the process mu goes to mu minus goes to E minus mu E bar mu. So baryons, as we know, an example is n going to proton plus E minus plus mu E bar. So obviously on the left hand side you have baryon number is 1, and here baryon number is also
1. But in this example, of saying individual electron number is 1 number, B minus is going to.
yes. Yeah. But the particle type changes. See, in contrast to the neutral current where the particle type doesn't change. So here the particle type changes, but each so you have to introduce a separate electron number for each type. That's fundamental. So this is obvious at the level of the baryon like this, but if you know that neutron is made up of a U DD and a proton is made up of a U UD, that means that each quark has a baryon number of 1 by 3. Okay? That that we have to agree that each quark has baryon number of 1 by 3. And we also know that the charges of the quarks, U type is plus 2 by 3, the D type is minus 1. Okay, so these are all the features of these interactions that we already know. So, and then, so this is the decay of baryon. But on the other hand, if you have a decay of a pion decays into, let's say, pi minus mu bar. So here baryon number is equal to 0, lepton number is equal to 0. Here L mu equals 1 and L mu equals minus 1. So the total L mu equals 2. Okay. Because the pion is made up of, pi minus is made up of U bar and D. From these charges, you can make out that this is in fact the story. But this is involving only the lightest quarks. So next to lightest quarks, what is the next to lightest quarks? Give me the name. Hmm? No, charm is significantly heavier, so S4. So in fact, the UDS is the sector where we have actually a pretty good SU3 flavor symmetry. SU3 flavor symmetry. Not only that, this actually is an SU3 L cross SU3 R. Independent chiral rotations, independent chiral symmetries, which is spontaneously broken to SU3 vector, where vector is 2, where the axial vector part which is n minus r by 2, is spontaneously broken. Spontaneously broken by what? By quark condensates. Bar condensate break this down. So what happens is that the SU3A is broken and gives rise to 8 proximate Goldstone bosons, which are the 5 minus 0, A naught, A naught, A plus minus. So this arises when mu equals md equals ms is equal to 0. So then this is exact. and approximate when this is not true, but retaining mu equals md equals 0 is much better symmetry, which is why mass of the pions is much smaller than mass of the pions. So mass of the S is significantly greater than mass of the U. So some of the decays, for instance, is K0 going to pi plus pi minus. Now, in contrast to this, so this is what is called, give me a name to this particular decay. This is a semi-leptonic decay. Why is it semi-leptonic? Because on the left-hand side, you have a meson, and on the right-hand side, you have leptons. So such decays are called semi-leptonic decays because it involves both baryons as well. Whereas this here is an example of a purely leptonic. Now, give me a name for this. In analogy to what I have written over there, give me a name for this. Hmm? Hadronic decay. Obviously, this is also semi-leptonic. Now, K plus goes to pi plus pi minus also. So from this, what can you say about the mass of the pion? Can somebody look up the PDG or something and tell me what the masses are of the pions as well as the pions? Somebody do a little bit of homework and tell me what are the masses of these particles. I think the mass of the pi plus we already said the other day. The mass of the pi minus, it is 139 point something. Something. Mass of the pi naught was 135 point something. Okay, I won't keep any significant cases. Then mass of the k plus minus, mass of the k naught bar, mass of the theta. Let's figure this out, folks. Please, somebody look it up and tell me.
K plus minus is 493.
493, okay.
0.677.
No, okay, let's just keep it. We don't go into the decimal. Okay, then
Not is 497.6.
497. Okay, then
K not R will be the same.
okay.
That is 547.
540. We also wanted to know what is the mass of the neutron and the proton. Let's write it down once and for all. Here, let me push the decimal places a bit more. 938 point. Somebody look up the mass of the proton for me. At least one decimal place. 98 point. I want to 27. Okay, then here
939.5.
56. Can you tell me the difference? MP, MN minus MP. Hmm? Yeah, just subtract one from the other. No. Okay, yeah. Tell me, what is it?
1.2.
1.29 GeV. I also need to know sorry, MEV, right? I need to know MN minus NP minus NE. Can you calculate this also and tell me what this is?
0.7.
7, 7, 8. Okay. What is the reason why I'm writing down all this? Now, all of you have looked at nuclear beta or neutron beta decay, right? We always talk about the endpoint. The endpoint is at 782 keV, and that is where you look for evidence of neutrino masses. Okay. So this is the excess energy that is available to you. So the electron that is emitted in the neutron beta decay can have a maximum of 782 keV if the neutrino is almost like zero energy maximum that it can carry. Right? So that's the reason for looking at this thing in great detail at this. So this is a number that is of importance in neutron beta decay. Okay? 782 keV, 0.782 MeV. Okay, good. Now I'm going to ask you a couple of questions and give you 2 minutes to figure out an answer. Why the mass of the neutron is greater than the mass of the proton on the one hand, but on the other hand, the mass of the 50 is less than the mass of the 5. Okay? If these guys are all made up of U and D quarks, all these are made up of U and D quarks, these are also made up of U and D quarks. Remember that in the pion sector, in the neutron and proton sector, there are no S quarks, right? U and D quarks. Why is it that it's like this? So what's wrong with the picture? Why is it that it's like this? Okay, then why doesn't it work for the 50?
I think 5 plus is an excited state.
No. It's not an excited. It's a pseudoscalar. So pseudoscalar means what? Q bar. Um, I'm talking to you. Talking to you. We say it's a pseudoscalar, which means that its spin is zero, right? And it's made up of two spin half particles. That means that the angular momentum of the spin is zero, and the total angular momentum is zero. That means that the orbital angular momentum is also zero, right? So that's not the explanation. The explanation is that there are two sources for the differences in masses. What are the two sources of masses? As my friend in the front row said, because the D quark, she already knows, is heavier than the D quark. The other reason is that they carry different charges. Okay, so there's also a dressing of the quarks by virtual photons. So there is an electromagnetic self energy of the quarks, whether it is in the baryon or it is in the meson. So there are two sources for the mass difference for delta n. Okay? And it works in one direction for baryons and works in the other direction for the mesons. Feynman has a famous paper, please Google it right now, on the proton neutron mass difference. Just Google it, it's there. So Feynman wrote this paper long before the quark model was there, and he didn't really know that constituents and so on. But he proved from first principles that if it was only the electromagnetic self-energy, then this relation could not be true. Okay? So this is the reason why you must also sometimes look at papers by these great guys, how they argue in less than 3 paragraphs, a very important physics question. Okay? So that's good old Feynman. So Feynman on delta n of the proton and neutron. So he proves that just the electromagnetic thing is not enough. Okay. So how does it work over here? Here again, it's in the opposite direction, but that's because it's just. See here. Notice. See, whenever we have a discussion of this kind, and as I mentioned in the WhatsApp group, this is a research course. So I will be mentioning things which are not there in books and textbooks and so on. I hope to be right, at least in the 95% confidence level. But you must think about what I'm saying, and you must think critically about what I'm saying. You see, here I gave you an explanation for this mass splitting, whereas here the explanation is not working in the other direction. So you have to ask yourself why this is the case. Okay. Now, why is it that this is true? Why is mass of the entire n 5 plus equal to any? So why?
Simply doesn't change the mass.
It's not just because of charge conjugation. It's the entire full CPT theorem, the full CPT theorem, which tells you that it has to be the truth. So this is a consequence not just to C, not just to P, not just to T, the full CPT theorem. CPT. Okay. Is there any other consequence of the CPT theorem that you think exists besides this silly observation that the mass of a particle and the energy particle have to be the same? Anything else?
Normalization of charges, electric.
No. It has nothing to do with arithmetic. It has to do with the gross properties or observables associated with particles, especially unstable particles. So that's the hint that I'm giving you, and I want you to think of what could be the consequence of particles that are unstable. Think of a particle that can decay into multiple final states. Okay. For instance, if over here, this K0 also could have a mode which goes into K0, pi plus pi minus pi 0, okay, for instance. So this K0 doesn't just have a two-body final state, it can also have a three-body final state. Is this allowed by all the data that we have on this blackboard? Is this allowed? And if so, why? Have a look and tell me why you think this is allowed. Supposing I want one more pi 0 over here, is it allowed or not? Why? Hmm? So the K is sufficiently heavy that it can decay into three ions. Now here I have given you an example where let's also see whether this is 5 plus, 5 plus, or this is a K plus. So what can I have over here? 5 plus 50 50. Okay, this is also. So here is a case where this K plus can decay into this, and then of course you have the charge conjugate states also, where you can have K minus going to pi minus, pi minus, pi plus, or it can go to pi minus, pi zero. And tell me what does CPT theorem, what can it imply for such decays? See, I can just stand in the blackboard and keep writing 2000 statements, okay? Not much point unless you people try to, march in step with me and try to.
The same DTA.
It's a very good guess, okay? But it's very counterintuitive, and it is the case that it's only the total lifetimes which are predicted to be the same. CPT theorem cannot tell you that this rate is equal to this rate and this rate is equal to this rate. It can only tell you that the total decay rates are the same for a particle. Very well. So if there are all these wonderful symmetries present over here, and of course I've already argued that they're not so well respected, nevertheless we can try to use these symmetry properties to make some sense out of this particle zoo. There are so many particles, and what are we going to do with them? And unless we organize them properly and give some structure to all this knowledge, then it's going to be quite difficult to deal with it. Okay?
So, what do you mean by total decays? Total of these two decays.
Not just two, there may be more.
All the decays.
All the decays. It's not an obvious thing. That's the reason why I was pointing this out.
Which is how the CPT theorem tells the decay rate, the total decay rate.
It has to be proved. Homework problem for you. It's discussed in TDV's book. You can have a look there. It's a very great book, fantastic book. Have a look.
Which one?
By T.D. Lee. T.D. Lee. You know the name, no? T.D. Lee is one of the guys who who proposed parity violation. Yang and Lee, they won the Nobel Prize in the 1950s for proposing that the weak interactions violate parity. He just passed away a few months back. Particle physics is good for health. You do it in your 90s.
But the touching material also.
That's I'm saying the same thing. Branching ratios or partial bits, the same thing. They are antiparticles. CPT theorem says that a particle and its antiparticle have the same mass. It also says that the total lifetime of a particle and the total lifetime of its antiparticle are the same, but it cannot say anything about individual branching ratios into allowed final states and the corresponding particle states. Okay, now I want to first start off with just the three pions, and I want to organize them along a straight line like this. And we said that the pions, 5 plus minus 5, 0, they form an isotriplet. Isotriplet. Okay? This word iso was introduced by Heisenberg in the context of isospin symmetry. Isospin symmetry. He introduced this name because the algebra that describes this isospin symmetry is the same mathematical structure as that of angular momentum and its spin. And the name iso is coming from the fact that he was talking about isotopes and isobars and a proton and neutron. Okay. So that's the reason why he introduced this word isotope. You know these words, isotope and isotone, right? E means that they have the same number of protons, isotone means they have the same number of neutrons. And it is useful in classifying nuclei. So you have uranium has many isotopes, U38, U35, etc. And it's all uranium because it has only 92 protons and the number of neutrons changes. That's why those are isotopes. You can have, say, 14 nitrogen, you can have 14 carbon, and these are isotones because the number of neutrons is the same, protons not the same. Rather, the sum is the same. So there is a relation between those isotopes. Okay, so please allow or help me organize the pi plus, pi minus, and 0 in along the straight line so that there is an operator associated with the isospin symmetry which can take me from one to the other. Help me. So we're writing a pi minus here, pi 0 over here, and pi plus over here, like this. So this is iso triplet, which means that this has J3 of minus 1, 0, plus 1. And the total J here is 1. Okay. And then you have a ladder operator that takes you back and forth like this. That's the J plus minus. And it has the same symmetry, same algebra as SU2. Very good. And someone tell me the properties of SU2. How many generators does it have? 3. And what are those? Well, I've already written them. These are the 3, JZ, J3, J plus minus. They can be written in terms of Pauli matrices. And then we have this great relation that J plus, J minus, J3, J plus minus commutator with J3 plus minus J plus. Okay, very nice. So this is an example of a Lie algebra with 3 generators, of which only one is a diagonal, and then you have a complex conjugate pair. And this has a very nice structure also, that this complex conjugate pair, when you consider its commutator, it produces the diagonal element, and then the commutator of this diagonal, J plus minus, produces an eigenvalue equation.
How you are relating your JP to minus 1 pi? How you are relating JP value with chart? If you had JP to minus
Just the name. So there is a relationship between, you have to give some label, no? You have 3 states. Okay. Call them pi 1, pi 2, pi 3, then you take a linear combination, call them pi x, pi y, pi z. But it so happens that you can identify them with the charged states. Good question, and that is the answer. So this is a very nice way of describing the SU2 algebra, which allows us immediately to generalize this to the next type group, which is SU3. Okay. How many generators does SU3 have? 8 generators. How many diagonal generators? SU3, two diagonal generators. And what are the names? Now this SU2 here is a subgroup of SU3. So obviously J3 will be one of them. The other one will be called Y, sometimes called hypercharge, and it also is related to the strangeness. So if it is possible to represent any representation of SU2 in a one-dimensional space, it would be possible to represent any representation of SU3 in a two-dimensional space. Now, this is for pi plus pi minus, but it's also possible to represent neutron and proton also on this neutron and proton, where this J3 is minus half and J3 is plus half, and then you have J plus minus, takes it back. Okay? Now, then we already know that the neutron is made up of two d quarks and a u quark, made up of two u quarks and a d quark. So it's also possible for us to say the d quark is here. Okay? Zero. So the quark model with the two lattice quarks can immediately be embedded into this nice symmetry just from our experience of what we know about neutrons and protons. And we also know what these things are made up of. It is made up of. This thing is made up of the u and the d bar, made up of u bar and the t. And this is made up of dd bar, u bar, 1 by square root of 2, and all that sort of stuff. So it has nothing, while this has plus minus. Okay. Now, one of you please help me trying to do something similar with this two-dimensional space and recalling what some of these particles are that we already have. Okay, I have written down and I have erased several particles, and I want to organize them in such a two-dimensional space. Mr. Chok, would you like to propose some particles that you want to organize on this plane? That we already did in this one-dimensional space. Okay. So my friend here is very clever. He wants to use his experience, and he says that, look, let's do this in this two-dimensional space. Let me draw one more axis like this, y, and then he wants me, I understand you right, read your mind. You want me to retain the same fundas over here. This is a pi minus over here. Okay. Then he says that, look, what about two more particles over here and two more particles over here in this SU2 subspace? And let's do that. Let's put a K naught over here. Let's put a K plus over here. What about here? Let's put K minus. Let's put a K naught bar, like so. And where is the last particle? There's one particle still missing. Theta. Let's put that also. Okay, very nice. So this gives an 8-dimensional representation of SU3 over here. This was like before. This is like the neutron and the protons in SU2 doublet, it's an SU2 doublet. Then the zeta here is a singleton with everything. And this is the best way of organizing in this SU3. Why is it that we are able to do this? We are able to do this because we have two diagonal generators, J3 and Y. And since we have all this kind of eigenvalue equations, we can figure out exactly what is the hypercharge and the third component of isospin each of these are. So how about giving a name to this? This is the pseudo scalar octet. There's also a baryon octet. So once again, Mr. Chuk will tell me that there's a neutron and a proton over here. Like this. And then now we have to start finding other particles. Now this unfortunately is only a doublet, so we have to get a triplet somewhere, and we will get a triplet like so here, and then we get another triplet. And what are all these particles that we have over here? Give me a name. Sigma. So this is the sigma. You have to figure out the charges also. As you're going down, the electric charge will also increase. Okay? So this will give me a sigma minus. Why? Because you have replaced one of the u quarks with an s quark. And the charge of an s quark is also equal to minus 1 by 3. That's why this gives you a sigma minus. What do you get over here? sigma naught, and here sigma plus. And here chi. Cascade. And how many? Two minuses. No, if I'm not mistaken. No, one minus one. Okay. And here this is the sigma naught. What about, so far we found only 7. What about the other one? Okay. So let's give a name. What should we give a name to this one? Baryon octet. Now, what is the spin of a neutron and a proton? Hmm? Spin half only, right? So this is the J equals half. However, these things are made up of 3 quarks, right? So two of them kind of cancel each other's spin and only a half is left. That is why this is the J. So there's one more thing you can do is you can try to line up all the 3 quarks spins and then you get something different. For instance, if you take the quark content over here and then you line up all the spins, then you get another particle with all the spins pointing up. And if you have 3 spins pointing up, what can we call it? We can call it J equals 3 by 2. Okay, like that. Okay, so what would then be the corresponding counterparts of this? So this thing would be here, delta 0, and then this would be a delta plus. Anything more? See here, you have 3 quarks, no? So why could we not put 3 d quarks and 3 u quarks over here in the J equals 1 half? Something that you should ask yourself. We have 3 quarks. Why don't we have a baryon octet? Why doesn't it have 3 u quarks, 3 d quarks? Why not? Because of Fermi statistics. Okay? These things here have no orbital excitation at all. So that means the spatial part of the wave function is completely symmetric under the interchange of. Okay? Then there's a spin part. So the spin part has to be antisymmetric in order for the total wave function to be antisymmetric. And if you have 3 identical particles, you cannot antisymmetrize. Okay? So that's the reason why you cannot do it over here. However, you can do it over here because there is a yet another hidden quantum number which is called color, and you can anti-symmetrize the color part, and then you, because now the spin part is symmetric, okay, all 3 spins are pointing up. So the spatial part is symmetric, the spin part is symmetric, color part is anti-symmetric. So if the color part is anti-symmetric, then it is possible to have 3 identical quarks sitting in the same state. So then you can do that over here, and what do you get? You do that delta minus, which is made up of ddt. So this is ddu, ddu, and finally here this is the delta plus plus with a u. Okay, so this is the first sign that there must be some hidden quantum number. Okay, so if this course is on the standard model, I tell you what are all the reasons why we are impelled towards a new quantum number which is part of the standard model known as color, whose theory is quantum chromodynamics. None of that will make sense unless I tell you where such a quantum number is coming from. And the earliest evidence that there is such a quantum number comes from the baryon spectrum. The fact that you can have states like delta plus plus with j equals 3 halves and strung out like this. So this is obviously isospin j corresponding to what this one. So this is 3 by 3. J is 3 by 4. Okay, now we start replacing each of these quarks by a single s quark. When you're going down here from this level to this level to this level, you're increasing the number of s quarks. Okay. Similarly, when you start over here, you start decreasing the number of, rather you start increasing, wait a minute. Here you increase the s quarks, here you just decrease the s quarks, or the other way around. Okay. Now you're going to replace one of these by the s quarks. Now when you go down, you increase the number. So what happens when you increase the s quarks? You get to get a counterpart of these guys with one of the S words. And we have to give a name. How about giving a name to this? And then there'll be two over here, like this. Let's give a name to these guys over here. Please look at this and give a name. With a star. The star basically indicates that it has much more energy. That's where the star comes from. Similarly, for the pseudoscalar object like this, there's a corresponding vector Meson object where you start seeing stars. The stars means that it is, as somebody just mentioned, it is an excited state. Sigma naught star, sigma plus star. This is a chi star minus, I guess, star 0. And this one, last, omega minus. Now, I want you people to give me the masses of these particles over here. At least a representative. We will not look at the splitting, but tell me the masses of these guys over here. The masses of these particles. This we already have, and which I unfortunately erased. So, please tell me mass of the delta, mass of the sigma star, mass of the chi star, mass of the omega. Okay. I think here let's take the mass of the pion to be 140, mass of the kaon to be 495, and mass of the eta to be 500. What did you say it was? 5?
539.5.
5%. Or maybe. Okay. How about giving me here the mass of the sigma, mass of the lambda, and mass of the mass of the nucleon? We already know is 940. Okay. Has Google given any answers to us? Okay. Yeah. Delta 1230. Okay. This one 1680. Okay. Which one? This one is 138.
Yeah.
Yeah. So this was wrong. That's why I was not convinced by this. 13. Okay. This is 16. 16.
That is 153.
1532. And this one 16. 7. 0. Let me round them off. So, here I would like to propose a relation for you, and I ask you to predict mass of the eta using the relation that this is equal to 4 times mk squared minus m5 squared divided by 3. Please predict mass of the eta. Take out your pocket calculators or whatever calculators. Tell me what is the prediction of the mass of the eta from this formula. So this is called the Gelman-Okubo mass relation. Gelman mass relation. You can basically say it's 4 by 3 mk squared. Is m pi squared is going to be only a small fraction. Okay, it's very small compared to this, and this is multiplied by 4, so we don't care about this. So 4/3 500 is how much roughly? 4 by 3 times 500. 2000. How much?
666.
Oh, then something is wrong. Oh, then I have to take a square root. Yeah. Yeah, please take the square root of that. So I need mass of the eta, and eta is roughly square root of 4 by 3 times NK, approximately. Square root of 4 by 3. 5, 6. Okay. So it's a reasonably good prediction. Okay, this is a prediction. Now, please note that this is a quadratic relation. Okay? Quadratic relation. And this is supported by the fact that we are viewing these as zero scalar, this zero scalar octet as approximate Goldstone bosons. If Goldstone bosons, then there is a quadratic relation this time. Quadratic relation. In contrast to this, where we will have linear relations. Linear relations. So here there's a more complicated linear relation. So let us try to compute m of the lambda. Now you people haven't given me these numbers. Okay, please give me these numbers.
Why is there quadratic?
Because these are Goldstone. I erased that, no? The discussion over here, where so this is saying something about the ground state of UCD. Why these particles, how the particle generation, mass generation takes place. It takes place because these are approximate Goldstones. M sigma, M lambda, M
Is around 1190.
1190. Okay.
M lambda is around 1115.
So it's lighter, okay, than this. Cascade. High, sky. It's capital high, but it's a cascade.
Approximately 1315.
1315. Okay, so the corresponding relation over here is m lambda is 1 by 3, 2 times m nucleon plus m pi minus m sigma. Okay, so please predict the lambda mass from this. Okay, this I'll leave this as a homework problem, but here it's easier. So can you tell me the differences between these two? This delta, and this delta. Delta of these two, delta of these two, delta. Yeah.
How how is that calculated? You included since they are Boston, yeah. You're getting quadratic. Why exactly the
Quadratic.
quadratic?
Yeah. So that you have to study a little bit. It has to do with the symmetry properties of the underlying Lagrangian and how the mass generation is. These are all explained in all these thousands of books that my office is sinking under the page. There will be a black hole formation pretty soon, centered in my office near my table. Because of the weight of the books, the short shield radius is just collapse like that. However, if you're still outside my event horizon, you can come borrow the book, read it in my office, and give it back. Never trust students with books because there's information loss and so on. Okay, please calculate. Come on, guys.
Approximately by approximately by 50 points.
150, he says. So my genius friend says that they are all approximately the same. So what is the reason for that? The Spock, number of Spocks here is 1, number of Spocks here is 2, number of Spocks here is 3. Okay? So this means that essentially the mass difference when you go from here to here, here to here, here to here, is because a more massive quark is being added. Okay? Now this is very beautiful. I haven't given a name to this. How about giving a name to this? Baryon decuplet. Now this is a very simple Gell-Mann-Okobo relation for the baryon decuplet. There was no complicated factors of 2, 3, nothing over here, no quadratic, nothing. Very simple. Okay? And the reason for that is that the decuplet is a very simple representation of the SU3 group. Now have a look at this and have a look at this and see what is the gross feature that you see that is different over here compared to what is over here. There's no state with any additional multiplicity. Every single state has unit multiplicity over here. So this is a very simple representation of SU3. So there are no complicated Clebsch-Gordon coefficients when you compose or produce such a representation from the basic representations of SU3. Okay, so because of the simplicity of this particular representation, the mass relations are also very simple. You have a beautiful mass relation like this. And the omega minus was not known at the time when Gell-Mann did this calculation. His Nobel Prize was for predicting the existence of omega minus and also for predicting its mass. He knew these are things. And so in case you didn't know, you should know, you should have some general knowledge. He proposed the Bock model right here on this campus, the old physics building. He had come from school and he predicted the Bock model when he was visiting us in Bangalore.
Sir, gigaplet has 10 elements, but generators are the state, other offsets also are the state.
Representations. So when you go to SU2, you know how to build up representation. I will talk about that also. I'm going very slowly in this course. Why? Because now I'm too old to go very fast. That's the real reason. But I also, the purpose reason is I want you to understand slowly all the things. Right? Okay, now let me take a break for 2 minutes and I'm going to ask you to plug in numbers and predict for me what the mass of is. Calculator. You have your phone. Should have a calculator on it. Actually, I should calculate this on Python. What's the point in doing it in a calculator?
Yeah, it's approximately correct. It's 1106.
Very good. So he is convinced that this is correct. Now I'm going to ask you a couple of very annoying questions. Okay. Now you guys gave me the correct explanation for the mass differences. What about the mass itself? Where is it coming from? What's the mass of the U-port, roughly? Hmm? 5 MeV. That's very small. If you have 3 times 5, that's 15 MeV. But the mass of the proton is 938 MeV. Where is all that coming from?
No,
Hmm?
interaction.
Yeah. It's an unsolved problem. Nobody knows where the mass of the protons is coming from. We, of course, keep it under the rug and so it's confinement. It's all correct. By the way, when you say 5 MeV, what do you mean by 5 MeV? Now, if you look at the definition of a mass, how do you define mass? Mass is a property that is associated with a particle state. Okay? What are the two properties that you have to associate with any particle state and why? Yeah, in the restraint mass, we don't use this expression rest mass anymore, or old textbooks. We use this, doesn't matter. But when you say mass, you're assuming that there's a restraint. Go, then a particle has a mass. Okay, what else is the property that you can define for a particle? Charge is because of the presence of electromagnetic interaction. So we don't think about that. Spin. Spin is very good. Why? It's related to a space-time symmetry. So mass. Isn't it? So any particle state ultimately is described in terms of its representations, irreducible representations under the Lorentz group or the Poincaré group, which is a bit larger. So why is it there are only two invariants? See, we already introduced the notion of symmetries and all. Also try to make it a little more.
You said that mass is related to space.
It is p squared. It is the ideal state of p squared. It is one of the two Casimir invariants of the Lorentz group. The first one being p squared, and the other one is something that's known as the Pauli-Lubansky tensor, which is related to the spin. Okay. So these are the two things that you need to know whenever you're talking about some particle. Okay. So we have a particle with spin 3 halves. How many polarization states does it have? 3 halves. How many polarization states? 3 by 2. 5 by 4. 4. 2J plus 1. Sure. Always.
If it is mass.
Exactly. So that's the caveat. If it is master, then you have to take this one. Otherwise, what happens? Why? Because if a particle is massless, there's no rest frame. Okay. So the way in which Wigner described these representations, which is the correct way of describing, is to break up these representations into various classes. One of a massive particle and one of a massless, therefore light-like particle. And there they are quite different. And so if it is a massless particle, one of them is already known, massless, no mass. So the 2j plus 1 in that case, you don't get all the 2j plus 1, you get only plus j and minus j. So if you have a graviton, what are the possible allowed spin states for graviton? Plus 2 and minus 2. Okay. You have a photon, plus 1 and minus 1. You have a gravitino, plus 3 by 2 minus 3 by 2. Okay. So that's how it works. However, in the theories that we are going to be dealing with, which is gauge theories, you start out with a massless gauge particle, which has only 2 degrees of freedom. Then you have a Higgs mechanism. Then the particle becomes massive. Then it must have a third degree of freedom. And where is that going to come from? It's going to come from the scalar sector. The scalar sector will have to contribute a degree of freedom. So you see, on the one hand, you may think that this is always operatic, it uses the representation and all that, but it has actual implications when it comes to the construction of this. So you people told me, and correctly so, that most of the mass of the baryons comes from the strong interaction. Okay, quarks, gluons wrapping around and they bash into each other and then they just don't like each other and they try to stay apart, which is what makes it very massive, and it rises all the way from about 5 MeV to about 940 MeV. But then there's one more thing. This whole construction of Wigner, it rests on the necessity and the need to have particles existing in asymptotic state in order for you to actually define this p squared operator. Okay. Now, these poor quarks and gluons are sitting inside atomic matter and they are confined, then they will never be in asymptotic states. Okay. So, when you say mass of a quark, it's actually only a theoretical parameter. It's not really a mass parameter. It's something that we all need to agree on so that we can communicate with one another. And you have to specify the mass parameter at some energy. So if you look at PDG, please go to PDG, and you look at the section on quark masses, and you tell me how they report the mass of the quark. The PDG started out being the spin about 50 years back. Now it's about that. And now they've even stopped printing many of them. Just say go online.
So what do you mean by asymptotic states in that?
And the particle has to be having Lee, that particle that is here, it's never alone, right? Because whenever you try to pull a quark apart, the notion of asymptotic state is necessary in the LSZ formalism field theory, where you can have a situation where you can turn off the interactions, okay? Where you have eigenstates of the free Hamiltonian. But we know that that's not possible with the strong interactions, because on the one hand, they are asymptotically free, on the other hand, they are confined. Exactly. So this is some convention where it is agreed upon that quark masses are reported at a certain energy, and then they evolve with the corresponding uh, RG evolution. Now, please tell me, these things are drawn on the same line over here. How is it that this thing was only 940 MeV, whereas this thing here is at 1230? It's like 300 MeV difference between this and this. Why? Where is that coming from? Because let's look at the neutron and the delta naught. They have the same quark content. The only difference between these two is that here you have du, one up, one down, like this. And let's say the other is up, or we can also have the other way. Whereas here, all the spins are pointing up. So where does this difference come from? Why is this thing 300 MeV heavier than this? Can you imagine 300 MeV? What a huge energy that is! Is more than double the mass of a ion. And that is the energy that it costs for you just to take the spin and to just push it up. Why? Why should it be so cost you so much energy? And what kind of energy is it? Now, spin is always associated with magnetism. So here, this is not the magnetism of electromagnetism, but it's the chromomagnetic energy. Just as the electromagnetic field has electric and magnetic components, the corresponding mu nu of QCD will have components that you can identify as an electric light and a magnetic light. And these magnetic energy is so enormous that it's 300 MeV just to line up the spin. So if you do produce a delta plus in uh, some collision, so what happens is this delta plus is produced with all the spins, then this it's too unstable. So what is the favorite decay moment of the delta naught? So you have to think about these things also. All of you have done part of this course. Exactly. So what kind of a decay is it? It's not decay. It's a not, right? It is not no W boson, no photon, nothing. And we said that it's chromomagnetic energy, which means that it's a strong interaction. Very unstable. And you are able to emit a ion because it is only 140 MeV. There is enough energy for you to produce a ion and this thing immediately. You don't need that. I don't think so. There's always angular momentum, orbital angular momentum. You're asking an important question. Then you can go and check. I don't think it's needed because you also have the activity associated with the wave in which it's produced. But check it out and get back to us as to what the exact decay of delta naught is. Is it there in PDG? Delta naught, what is the decay? We have enough time here, so I know you, whatever question comes to your mind, you just check it. You can find an answer.
It was P plus
Hmm?
primary decay is P plus
P plus pi. But it can also go to a neutron and actually, the ratio is given by group theory factors. So that is the very good thing. So which brings me to the next point. Thank you. it's not just about drawing these nice charts and being very happy that we got this. If there is a real underlying similarity, it should also determine some of the dynamics or at least relate various dynamical pieces of information. For instance, the decay rates. So that particular two decays that you mentioned, the ratio and the branching ratios, are actually group theory factors. Okay? So if you look at any standard book like Griffiths, one of the problems that we listed will be to compute that particular ratio. Check it out. So, in our discussion over here, which was just the SU2 part, we went from here, and then we said that the quarks need to be organized in this particular way, and since everything is built up of quarks, you can get the neutrons. Now, here so far we have not mentioned the quarks at all in terms of building up these states. So now one of you has to help me build in this same space of hypercharge here, put the quarks that are of interest to us. This we already know, U, no, P and U. How about one more quark? Where should we put the quark? Hmm? S here. And why should we put it here? It has no idle spin, the S quark. It has only strangeness. And the unfortunate convention is that the S quark has strangeness of -1. Okay? Conventions of this. So these are the quarks. But there are also antiquarks, no? So what about antiquarks? What should we do with the antiquarks? Antiquarks would be C bar, no, I think it'd be here. U bar, yes. And here, S bar. So you have one triangle like this, and this transforms as a 3 of SU3. And what does this transform as? What does this transform as? E bar. How come we never talk about 2 of SU2 and 2 bar of SU2? How come we never talked about that? Hmm? How come we never do? They are equivalent. So in SU2, there is no bar representations because they are there, but they can be brought back into this form through a similarity transformation. Okay? So it means that every representation, so if you start with a two-dimensional representation, you can generate every representation of SU2 by tensor products. Okay? How do we know that? You can start with a spin half, take a spin half, then what do you get? Take a spin half, you get a spin 0 and a spin 1, right? Then you take a spin half and a spin 1, etc. So every representation of SU2 can be obtained by starting with spin half or a two-dimensional representation. Everything can be generated in that. Not so for SU3. It's already so. The whole point is SU3 is the first semi-simple Lie algebra which has sufficient structure that it starts showing some interesting properties. SU2 is so simple that it doesn't have any real way of getting generalized, whereas SU3 has enough information to be able to get. So from a 3 and a 3 bar representation, you ought to be able to get the 8-dimensional representation, right? Because these things here are built up of a quark and an antiquark. Okay? So the 3 times the 3 bar should be able to give you what? Should be able to give you union 8 plus 1. And this 1 is what is called an eta prime. Eta prime, eta prime. Let's also add it over here. And then in that case, we can make this the non-edge. It's not really a member, but in the past, they used to take it. How do you know that 3 times 3 bar is an 8 plus 1? Hmm? Right. So you want to do that? Or you want me to do it? I always is unloading his work on me. So this is a three-dimensional representation, and this is a three-bar representation. So let me write three bar times. Okay. So this is like this 1, 2, 3. So this is a 1, and this is 3 times 2, 3. How do I know that? This is a 3, this is a 4, this is a 2, and I draw a hook through this, and it passes through 3 of the hooks. Rather, the hook passes through 3 of these boxes. Let me explain this for any SUN. Any SUN, this is an n-dimensional representation, and this with n minus 1 boxes is an n bar. Okay. So that also you can see. For instance, here we write n minus 1 on the way through, n minus 2. Then you draw the number of hooks, and then the only thing that will survive will be an n minus 1 number of hooks that you draw. So the way in which you compose these things is the same thing. You add one to this, and then you add one at the end. If you add one at the end, it is n of them, n boxes, so that is 1. Okay. Here it is n plus 1, n minus 1. So n times n plus 1 times n minus 1, dot dot dot, and then number of hooks that you draw gives you an n times n minus 2, etc., giving you n squared minus 1. Okay. You have to work this out for yourself. So this is what also shows you that for SUN groups, n times n bar always has the adjoint representation. So this is the adjoint. So this is simple. Now let's see how to get this decuplet. And now I need a volunteer to do that. Any volunteers to do? The decuplet is obtained from 3 quarts, right? So we need 3 times 3 times 3. Okay, so let's do a 3 times 3 box times box. Okay, so this is box plus. What is this now? 3 bar. 3 bar. We already know that. This is 3 times 4 by 2, which is 6. Okay. So 9 adds up to 3 bar plus 6. Fine, very good. So now I need a 3. This plus this. I have to now multiply it with the box. So what do I get now? I get this plus this plus the same. Okay. So this we already saw is 1. What did we say this was? 8. 8. And this is 3 times 4 times 5 divided by 3 times 2. So you see, you have got the baryon octet and you have got the baryon.
What are the additional ones?
They're just there, they're of no use.
How do we know that?
Maybe there are other exotic states or something. I don't know, it's a good question. So we have covered a lot of ground today, at least in my opinion. We have shown that there has to be an additional quantum number for color. We have already grappled with things like the S quark mass, and we know that the UND quarks have very small mass, and we know how to compose and produce all these baryonic states from the quark model. And we have also run into a little bit of group theory. We have done Young's Fellow, calculated all these irreducible representations. Is everybody with me, or some things are not completely explained? Everybody here understand what I'm saying?
So why should it be that the baryons or the wisdom should be that representation of this?
Because we are saying that that SU3 is a good symmetry of the strong interactions. What does it mean to say something is a good symmetry? How do you know that there is rotation symmetry? You say that at hydrogen atom, the states form orbitals, sp, d orbitals, and then these have the same energies and they are energy degenerate. It means that the YLNs, which are representations of the rotation group, form a good eigenbasis and states can be classified in terms of the YLNs, right? So here if we say that SU3 is a good symmetry of the strong interactions, then whatever we see, matter that we see, had better respect the constraints dictated by the underlying symmetry, which happens to be SU3, but which is spontaneously broken in the sense that it is produced Goldstone bosons, but it also the baryon sectors still respects this, etc., etc. Okay. Now this is the JP equals minus half, half with a minus. Okay. There is no counterpart of half plus. There are no parity counterparts of this. And the reason for that is that part of the symmetry is spontaneously broken. That because the SU3 axial vector part is spontaneously broken, there is no reason why there has got to be half plus. So these are all the puzzles that were solved by studying the symmetries of the strong interactions. You postulate a symmetry, then it makes some predictions. Predictions are violated, and you say, oh, violated, where did it go? Okay, it's spontaneously broken. See, today all this seemed very obvious. When Nambu and company were doing these things, they knew nothing. They start from scratch. His idea of spontaneous symmetry breaking in 1960. Okay? And the strong interactions were just being developed. So S-quark was discovered only a few years before that in cosmic ray showers. And the pion was discovered only in 1947. It's a very recent discovery. The progress that we have made has been exponential. So that is why all these things seem, oh, it's so straightforward and it's trivial. It's not so. It wasn't for them. I mean, that's the greatness. Hardly any, real piece of information and nothing to guide them to solve all this.
Symmetry is spontaneously broken. Why do we not have half plus?
Because no such symmetry is there. It's spontaneously broken.
It is broken from some previous symmetry, right? So there should be
full SU3 vector times axial vector is the full symmetry of the Hamiltonian. Okay. Now there are different ways of looking at symmetry also. There is a very naive way which is saying, I'm only going to look at the Hamiltonian and it has a symmetry. But in quantum field theory, something very amazing happens, which is that even if the Hamiltonian has a symmetry, the ground state in the Hilbert space may not have that symmetry. And that's the whole point of this. If it is realized, it is known as the wild realization of a symmetry. Wild as in one wild, not as in wild as in okay? That's a wild realization. The other realization is called the Goldstone realization of so-called spontaneous symmetry breaking, which is actually not very good notation. So we would rather look at it as a Goldstone realization, that is, the Hamiltonian has a symmetry, but the spectrum does not have this.
There should be a symmetry breaking field that produces.
That is the quark condensate. So you don't need an external field, but the ground state selects a broken phase. Why? We don't know. It is a way of describing nature. And if you put all these things on the lattice and you change the temperature and all, you can even have pilot symmetry restoration, okay? Which just doesn't happen in the real world, but it can happen on the computer. Or it can happen under very special circumstances like a Big Bang, LHC, where you have Alice experiments, very high energy, high density. The next walk is the jump walk. It is actually also possible to organize the particles that have a jump walk in a three-dimensional space. And I would like you to have a look. Please Google SU4 jump walk jump stakes and see. Do you find it? Just say SU4 jump. Look for images. Yeah, here. You see, here are some beautiful pictures. Over here. Ah, so for the color. Yeah. You see, this is a three-dimensional space, and you can see various planes. Okay? So what you have here is the number of jump walks increasing along this axis. So just as the omega, there is a corresponding omega plus plus with three jump walks. Then you lose one of the jump walks and replace it with one of the other walks, then you get this plane, then you get this plane, then you get this plane. Okay? So here there are no X walks, but only U and D walks are being introduced. Now we have a greater chance also, we can also introduce this one. So I think even that is done. So it's possible to organize to one more. Let's see, let's click on this one. Of course, the symmetry is not very good, but you can still organize your particle spectrum. You see, here's a beautiful way of organizing in this three dimensions. But we can't go ahead to deep walk and do this because there's no way of representing four axes on a plane. Okay? But this already is telling you that this SU3 can be generalized to SU4 rather than IC3. Okay? And we will do a little bit of that mathematics also in the next class. So let's meet on Tuesday. I'm sure none of you here is going to observe Shankranti. So let's meet on Tuesday at 10 o'clock. Okay? And early breakfast in town. Are you all taking today's class also? The same class that comes in pieces? Or some of you are leaving and others are coming? So if Sudhir is not teaching, I may steal a little bit of his time also. Tuesday. Because I'm likely to miss a couple of classes in February, so I just want to make sure that we don't lose anything.